All right, so welcome, Jesus and Bradley and Ralph and Victor and Cesar, and those who are all watching this or coming soon. This is yet another linear algebra lecture, and let me talk about what we're going to do. So let me share my desktop. Okay, so here's the plan today. As always, we'll start out with questions if you have questions. And then after that, we're going to get into symmetric matrices and dot products. So we're going to be looking at dot products. Dot products happen a lot, and we'll talk about how they relate to symmetric matrices. And then we'll get into eigenvectors are orthogonal. It's a very important theorem, and we'll be able to see why that's true. Then skew symmetric matrices. And then after that, we'll get into orthogonal diagonalization and principal axes. And then we'll talk about triangulation. Instead of diagonalization, we can talk about triangulation. And then we'll get into the singular value decomposition. And then finally, rank and singular values. Okay, and we'll probably also do the Cholesky decomposition, but we'll see. So that is the plan of today. I want to mention something. A week from today, there is no webinar. How come?
It's the exam.
Yeah, it's the exam. So it's time to start thinking about it. I have written the exam. I did it over the weekend, and I haven't taken it yet. That'll do in a couple days. But the exam is coming up a week from today. Same kind of format as your last exam. So it's going to be a paper and pencil exam, and you take a picture and then pop it on Canvas is the way you'll do that. So same as last time. So that is the plan for today. Again, that exams are important. Take them seriously. Practice, practice, practice. And don't just practice only doing things with matrices. Make sure you practice written arguments. Okay, so proofs, in other words. So there are going to be a bunch of those, and you need to be able to do that. So are there any questions that you might have? Over 19. So let me look at it. Just one second. Okay, so here's the one you want, right? 13 a little after, but first 19. So we want to find the solution to the initial value problem. Xy equals 0, -1, 6, 5. Sorry, xy prime equals 0, -1, 6, 5, xy. Okay. And the question is, the hint is, form the matrix exponential e to the at, and then the solution is e to the atc, where c is the initial vector. And that actually came from calculus, second quarter calculus, where you had to solve a differential equation. And you realize that if you had y prime equals ky, then the solution was, do you remember? Y equals, let's see, y'all jumping in.
ky squared plus c.
Not ky squared plus c. That won't work, because if you take the derivative of ky squared plus c, you just get 2ky. And 2ky is not equal to a constant times ky squared plus c. you remember?
So
Y
y to the k plus c?
No, not quite. It was a biggie. The hint is it relates to what we're doing on problem 19. CE to the KT. Do you remember that? So that happened in second quarter calculus. I know it's been a while, but it was a biggie. Basically, you divided by y and you integrated both sides. The integral was log, and you solve for log by e. And that's where it came from. So what we want to do is basically the same thing, except instead of y, we have a. And it's no different. So that means a is equal to CE to, it's going to be like a CE to the KT, except that doesn't quite work. Okay, it's going to be a E to the AT times C. So it's not a K anymore, it's an A. So it's Y equal E CE to the KT. Okay, the way they write it is E to the AT times C, because it actually matters left and right. And typically you can always, at least in second quarter calculus, you can always write it as times C that way. And then when you do the matrices, it'll actually work. So what we need to do is we need to find E to the AT. Any questions on that? Any questions? Okay, so what is E to the AT? How do we find it?
We diagonalize A.
Exactly. We got to diagonalize it because we can write E to as a power series, and then we can diagonalize. So, and then we diagonalize, and then it'll all work nicely because powers are much better when it's diagonalized. Okay. So how do you diagonalize this matrix?
Find its eigenvalues.
Yeah, find the eigenvalues. We have a 2 by 2, so I'm going to use the formula because it's a lot easier. Again, you can do it the longhand is fine too. So we know that lambda squared, and then minus what?
The trace of a.
And what's the trace?
5.
Yeah, so 5 lambda. And then plus.
Its determinant.
And what's the determinant?
6.
6. Okay, 0 times 5 minus 6 times -1, and that's 6 equals 0. Any questions so far? And they're very nice to us because this factors beautifully. So hopefully you can factor this in your sleep also. It's lambda minus 3, lambda minus 2. Equals 0. So what are the eigenvalues?
3 and 2.
Yeah, so 3 and 2. I'm going to write 2 and 3 just in numerical order. It looks a little better. Any questions so far? Easy enough? Okay, once we found the eigenvalues, now what do we have to find?
The eigenvectors.
Yep, we got to find the eigenvectors. So let's find the eigenvector corresponding to 2 first. Just do it in order. So that means we subtract 2 from the diagonal. Okay, and let me do that. So I'm going to take I'm going to take the diagonal. I'm going to subtract 2. I get -2. And then -1. And the bottom, I don't care. 0, 0 is fine because we are RAFing it anyway. Any questions on that? Okay, so what is the eigenvalue? So what is V sub 2?
-1, 2.
Yeah, -1, 2 will work. But I'm going to make it a little different, but we'll start with -1, 2, and then we'll play. Okay. All right, so it's -1, 2, but how can I make this better?
We need to normalize it, so multiply by 1 over the magnitude.
Yeah, if we normalize it, then things get a little better usually. So we're going to normalize, multiply 1 over the magnitude. The magnitude is 5. Are y'all following that? So it's 1 over root 5. And similarly, we'll have a 2 over root 5. Any questions on that? Makes it a little better in terms of finding the inverse. Okay, now we got to do the same thing, except we got to find V sub 3. So I'm going to copy and paste and then adjust. So V sub 3. And I guess I should do some more. Notice we are subtracting now 3 from the diagonals. So that 0 now is a -3 instead of a -2. So what is V sub 3? Very similar.
-1 over root 10, 3 over root 10.
Yeah, let me write it in pieces though. It's going to be, so -1, 3, and then the magnitude of -1, 3 is 10. So that means -1 over root 10 and 3 over root 10. Any questions on that? Okay. Are these orthogonal, by the way?
Yes.
V2 and V3? Yeah, they don't look very orthogonal, do they? If I dot them, I get 7. Any questions on that? So what happened? Why are they not orthogonal? So I figured I'd go through this. What do you notice? Let's go to the original. Can anyone tell me? I don't see y'all jumping in. There's a theorem we had last time. I'm not hearing it. Okay, you only get orthogonal when you have symmetric matrices. Do you remember that? So I wanted to do this to kind of express a point, is symmetric matrices are much better because this whole dividing by root 5 and divide by root 10 doesn't really help us much because we don't have an orthogonal matrix. Any questions on that? So I did that just to kind of like walk you through it and then realize, no, that didn't help at all. Might as well use -1, 2 and -1, 3. Any questions on that? Because we don't have an orthogonal matrix. Okay, but what we can do is still do it. We can still diagonalize it, just won't be orthogonally diagonalized, which is not a problem. So P, let's write this out. P is going to be the matrix of the vectors. And I'm going to use the easier ones. Negative 1, 2. And a negative 1, 3. This makes it a little easier.
So if we do not have an orthogonal matrix or a symmetric matrix, we don't have to use the normalized eigenvectors.
Right. And in fact, the whole point of using the normalized eigenvectors is so that you can just take the trace instead of the inverse, which is the inverse. Not the you can just take the transpose. Just take the transpose and that'll work. But here we don't have a symmetric matrix, so it doesn't work. So I'll just use the easy ones. Right. The whole point of orthogonally diagonalizing is because you can do the transpose and you don't have to worry about the inverse. Fortunately, with 2 by 2s, inverses aren't so bad. In fact, let's do that. So what's P inverse? So P inverse, let's do that. There we go. So P inverse is going to be what? Well, you take the determinant, remember? What's the determinant of this matrix?
Negative 1.
Yeah, negative 1. So it's going to be negative 1 outside. It's 1 over negative 1, which is just negative 1. And then remember, you switch the diagonals. So that negative 1 becomes a 3. And the 3 becomes a negative 1. And then you multiply the off diagonals by negative 1. So the 2 becomes a negative 2. The negative 1 becomes a 1. And now let's multiply the negative 1 through. And when I do that, the 3 becomes a negative 3. 1 becomes a negative 1. And the bottom negatives become positive. And there's my inverse. Okay, it's pretty easy to check that you got it right too, because you can always multiply them and get the identity. Okay, what's our diagonal?
2, 0, 0, 3, red as rose.
Yeah. So the diagonal is, 2, 0, 0, and a 3. Any questions on that? Is that clear? So now we can start writing this out. It's a bit messy, but we can do this. So we can now solve our system. And remember, let's go back to the original. We want e to the AT, basically, times c, where c is the initial vector. The initial vector is 2, 2, by the way, because they gave that to us. Any questions on that? So let's do that. So now what we can say, did they call it y? What did they call it? xy. So now xy is equal to, so e, remember that's a summation. And that's n, actually I like k because n is the dimension of the matrix. So k equals 0 to infinity. And then if you remember,
A to the k over k factorial.
yep. So we have k factorial. And then we're going to have a to the k. Okay, a to the k is going to be, well, we're going to take what? Remember how it works? How we diagonalize?
PD to the K P inverse?
Yeah. So it's going to be P, and it's going to write as P because I have it right above, so I don't have to type it again. It saves me time. P times D to the K times P inverse okay, and then of T. So what does that mean of T? So what does that mean?
Put a T, multiply with T.
So what does that mean?
Could be a parameter.
Yeah, so it's kind of a parameter, but how does that work? Yeah, the easy way to do it is when you work it out, you get e to the t basically. So let me write it out. So notice that what we get is this whole e to the t is this stuff, right? So the 2 and the 3, what do they become? When you add all this up, I'm gonna write of t just to show you. Oops, didn't like something. And then times, was it 2, I think they gave us? Yeah, 2. Sorry, it takes a long time to type this stuff. So 2. So when you work all that out, what you can do is you can rearrange this and realize that the P and the P inverse don't have K's in them. So they can get sent outside. So does a 2. And you end up getting the summation of d to the k of t over k factorial. And the idea is that's e to whatever you've got. So let me write that out because that might help to understand that. That's going to be P times, now let's write down the matrix. So now what you get is when you have that summation of d to the k, and d is 2, 3, that's going to be e to the 2t. That's what it all sums up as. And then we're going to have a 3, e to the 3t. 0, 0, p inverse times 2. Any questions on that? Okay, and if you want, you can, multiply these out, and then you'll get something. When you multiply the matrices out. But I don't know if I'm going to waste your time because it's taken a long time to type all this out. Typing takes forever on this. Did I lose you? Any questions? Okay, if there's no question on this one, I think I'll go on to number 13 because that was the other request. That was 19, so let's look at 13. So for 13, let me grab it. Ah, the sunny day. Unfortunately, it's on 2 pages, so it's going to be a pain to grab. but I think I can still get it. Let's see if I have enough room. Yeah, I think I can do it. It's going to look a little weird. Okay, so here's number 13. So the following table describes the transition probabilities between the states rainy, partly cloudy, and sunny. The symbol PC indicates partly cloudy. Thus, if it starts off PC, it ends up sunny the next day with probability of 5th. If it starts off sunny, it ends up sunny the next day with probability of 2/5, and so forth. First, you understand what this matrix is representing based on the question. Any questions on that? Okay, hopefully that means you do. Okay, and the question is, given this information, what are the probabilities that a given day is rainy, sunny, or partly cloudy? So what do we need to do?
Find the steady state vector.
Exactly, we need to find the steady state matrix. So we need to find the steady state matrix and then do a little more, but at least that's definitely the first step. So let's find the steady state matrix, and we're guaranteed that what is the eigen value if it's a steady state?
1.
Yeah, exactly, 1. So that means I can jump in and I can just subtract I. Is that clear? So let's do that. So I'm going to subtract I, which means subtract 1 from all the diagonals. 1/5 minus 1 is -4/5. And then 1/5. And then 1/3. And then we have 1/5. We have 2/5 minus 1 is -3/5. And then 1/3. Any questions so far? By the way, are these rows multiples of each other? Take a look.
Yes.
They're multiples of each other?
No.
Okay,
No.
If you say yes, you need to tell me what I need to multiply row 1 by to get to row 2. The answer is not going to happen, because notice the third entries are both the same. That would mean you'd have to multiply by 1, which wouldn't work. So they're not multiples of each other, and because of that, that means I'm guaranteed that when I RREF, I get zeros in the bottom. Any questions on that? Just to make life a lot easier, I am going to, I'm just going to multiply by 15. I'm allowed to do that because I'm RRFing. Then I don't have to worry about all these fractions. So if I multiply by 15, the first one becomes 12 or -12, and then 3, and then 5, and then 3, and then 9, and then 5. Any questions on that? Okay. And again, I could use Symbolab, but this isn't that bad. So now I could just multiply the second row by 3, add it to the first row. That zeroes out that -12. And then this becomes, this becomes a -3 here. And, oh, wait, I'm multiplying by 4. Sorry about that. Multiplying by 4 and adding it. that's not negative 3 anymore. So then I get negative 3 times 4, negative 12, and then plus 3 is negative 9. Okay, and similarly, I get a negative 15 here. Any questions so far? I just made that a 0. And then I can divide that by negative 3 here. This negative 9 becomes a 3, and the negative 15 becomes a 5. A little prettier. Now I can take the first row and add it to the second row. The negative 3 becomes a 0. So I'm just RREFing quickly. And this 5 becomes a 10. If I'm doing everything right. Any questions so far? Okay, that's good enough for me. Now I can get the answer. So what do I get? Oops. It doesn't want to be good. Oh, I know. I think it's going to the next row. I think I know what's happening. I think I need to put on the next page. Okay, so what do I get for my vector?
Negative 5/3 and negative 10/3.
Okay, remember it's a 3-dimensional vector, not 2-dimensional.
1.
Yeah, so you're letting z be 1. So if you let z be 1, then x needs to be negative 10/3. And y needs to be, let's see, is that right? If z be 1, yeah. And then we get 3/5. I'm sorry, 5/3. Okay, you could do it. I think I'd rather let it be 3 instead of 1. So I'm going to do that if you don't mind. So I'm going to multiply by 3. Then it's get 10, negative 10, 5, and 3. Yeah, it's negative 5. Thanks. Okay. I'm not done yet. Let's go back to the question because that's important to see. We want to find out the probability that it's rainy, sunny, or partly cloudy. Okay. So we need to find the probabilities. Let me make sure I didn't lose a negative somewhere. It feels like I might have. Do you see me losing a negative? Let me double check. So I multiply by 15. That's negative. Positive, negative, positive. That looks good. And then multiply by 4 and added. Aha. Let's see if I multiply by 4 and add. Let me go through the work. I'm a little worried about this.
I think that negative 3 in the 2, 2 spot should be a negative 9.
Where? Which matrix?
The third one.
This one right here?
Yeah.
Yeah, so let me double check. So we multiply by 3 and added. So this guy, again, this is negative 9. And if we multiply by 3 and add, we'll multiply by 4 and add, this becomes a 25. Yeah, I think I made a mistake on that step. Sorry about that. It's hard to type and do this at the same time. Okay, so that changes everything. Sorry about that. Actually, the 12 should be a 0, of course. And then I'm going to go ahead. So now I'm going to show each step so I don't make a mistake. So now what I'm going to do is kind of messy here. I have to, divide by 3 and subtract to get rid of this -3. So that becomes a 0. Let's see. So 3. Okay. I think the 3 -3 5 isn't supposed to be that. Wouldn't it be 3 -9 5? Let me see. That was the second step. Yep. That changes things. -9. Yep. Easy to make little mistakes. Okay, and that changes this next one because I'm multiplying by 4. 4 times 9 is 36. So that becomes a 33, doesn't it? -33. And a -9. Okay, yeah, good to show you each step because then I make one little mistake, the whole thing falls apart otherwise. Okay, and then you get more, you know what? It's probably easier to go to Symbol Lab. I'm convincing myself this is messy because now we got fractions and we can't get out of them. You can take the 3 and divide by 3 and make that a 1. Make that a -3. Make that a 5/3. That I can do, and I know that's got to be right. And then it becomes ugly. So I think at that point, you want to go to Symbol Lab. So I want to pop that in. Otherwise, I can do it, but so I want to pop that in and get the RREF. Okay, so 1, 0, 20 over 33. I'll trust it. And the next one, 0, 1, 25 over 33. And that should be negative, of course. Yeah, it looks a lot better. Okay. Any questions so far? We're almost done. See, I knew I had a trouble because you can't end up with negatives. That can't ever happen. That's part of the theory. So now I can get my matrix and my vector. Okay, and if you want, you can just let the z be 33. Makes it a little easier. Don't you agree? So if I let z be 33, and then we get 20 and 25. Okay, what's the last step? The hint is this is one possible eigenvector, but it's not the one we want. So what do we want? Okay, we need it to be a unit vector. So we're gonna divide it by the square root of 20 squared plus 25 squared plus 33 squared. And then we're going to do the same thing for the other two. Divide the whole thing by that. And those are our probabilities of the, was it sun? No, rainy, sunny, and partly cloudy. So the first is a probability of rainy, the second is a probability of sunny, and the third is a probability of partly cloudy. Okay, so it's more often partly cloudy. A little bit more often. Does that help?
Yeah.
Okay. I think I want to get to new material because it's longer than I usually go. It just was so long to type all this out. Okay, so I want to remind you a big theorem, a big definition, that A is symmetric if A is equal to A transpose. Do you remember that? Hopefully you do, because we use that a lot. And then A is skew symmetric. I don't know if I've used that word yet, but now we're using it. A is skew symmetric if A equals negative A transpose. Okay. So we have symmetric and we have skew symmetric, and they're really important. Any questions on the definitions? Okay, there's nothing to prove. It's just a definition. Now comes a theorem, and this is a pretty important theorem. If A is symmetric, then AX dotted, that's really the dot product, with Y is equal to X dotted with AY. So what's nice is that if we have a symmetric matrix, I can float that matrix from X to Y. Isn't that a nice little theorem? Okay. Any thoughts on how we might want to show this is true? So I got to at least prove a few things. The hint is, or at least the start, is you always start with the left and hope you end up at the right. Any thoughts on what I can do? Any ideas?
Just let A be a symmetric matrix and multiply with the X first.
Asymmetric and I multiply by X, but so what do I do though? What is this equal to, in other words? That's actually not what I'm going to use first. I'm going to use symmetric, but that'll be like second or third. Okay, the idea is the dot product can be switched and you need the direction, right? U dot V equals V dot U. Do y'all know that? Last quarter happened a lot, right? It doesn't matter which order you write it in. So I'm going to rewrite this as, instead of AX dot Y, I'm going to write this as Y dot AX. Any questions on that? Okay, so we could do that. Now, do you remember what AX is by definition? You remember?
Linear transformation.
It's a linear transformation, but it's a dot product. That's a hint. I mean, it's a...
A times X is equal to I minus A?
No, it's not equal to I minus A. It's a good try, though. All right, how about Y dot AX? Do you remember how that works? Or let's go AX. So AX is a dot product also. So the idea is what I can do here is I can take the transpose to play with this. What happens when I take a transpose? And remember, the transpose of a number is just the number, right? Do y'all agree? Right? Because if it's a 1-by-1 matrix and you take a transpose, you don't do anything. Do y'all agree?
Yes.
Okay. So if we look at, in fact, let me write it this way, is a little better. AX dot Y, that's going to be the matrix multiplication of going there. So that's going to be Y transpose. Remember, transpose switches things, right? Times A transpose. So times AX quantity transpose. Any questions on that? All right, but what can I do now? We're getting closer. Because I can take those transposes. What happens when you take the transpose of a product? Well, it switches them, right? So now we're going to be talking about Y X A transpose, but A transpose is A. So that's going to be Y transpose. And then we're going to have X transpose A. Any questions on that? I could write this as a dot. I forgot the dot. Oh, yeah. Dots are hard to find. Not the best dot. Let's see, that's not the dot I want. It's one of these dots. I think it's that one. There we go. Any questions on that? So we have Y transpose AX transpose, right? But now what can we do? Well, the idea now is we can untranspose, and now we could put the, now we can write AY. So let's get rid of that one for now. So what is, actually, no, I want that. So now what can I do? Now I can look at this dot product and say, hey, if you dot product by something, that means you're multiplying the matrix by it. So that's going to be X transpose, AY transpose. Because that's what it means to take a dot product, is you multiply by its transpose. But that is X dot AY. So it's just a lot of symbols, but it means that we can do this. Okay, so it's kind of a nice little theorem. Any questions on it before I move to the next one? A lot of theorems today. Okay, so this is a big theorem here, probably the biggest theorem of the day, and that is right here, is that if let A be symmetric and V and W be eigenvectors of A for eigenvalues that are not equal to each other, then V and W are orthogonal. Okay, that's a big deal. So V and W are orthogonal. All right, well, how do we show that?
We dot them, see if we get 0.
Okay, yeah, we dot them and hope to get 0. So let's do that. And we're going to do it and do more, of course. So we're going to take V dotted with W. Okay. Now the key is we know what V and we know that W is an eigenvector, right? Do you agree? So if W is an eigenvector, how can I rewrite W? Okay, we can write this as, remember that if W is an eigenvector, that means A times W equals lambda times W, right? So W equals 1 over lambda, which I can pull outside. Or I can multiply through even. It might be easier. So I can write 1 over, whoops, lambda. There it is. V dot W is equal to V 1 over lambda V dot, well, 1 over lambda, actually, I don't need the 1 over lambda anymore, is equal to V dot AW. Any questions on that? Okay, but we now know from the last little theorem that V dot AW is the same as W dot AV. Remember? Any questions on that? Okay, but what's AV?
Lambda V.
Except it's not lambda V, it's going to be a different one, right? So this is going to be W dotted with, I guess I want a lambda here, not a 1 over lambda. It takes forever to get to the lambda. Sorry. There we go. So it's going to be W dotted with, not lambda V, but some other thing V. And I'm going to write this as, how about mu times W dot V. Okay, but now W dot V and V dot W are the same. Do y'all agree? Lambda and mu are not the same. So what does that tell you about W dot V? If you're not sure, let me write it out. So what we can now say is that V dot W times, I guess I want times lambda, minus mu times V dot W, or W dot V, however you want to write it. The order never matters with dot products. It's not like matrices. So I have W dot V, but I can write that as V dot W. But now what can I do? Basic algebra.
Factor out the V dot W.
Exactly. I can factor out the V dot W. And when I do that, I'm left with a lambda minus mu times V dot W equals 0 because I subtracted, right? But lambda minus mu is not 0 because we have non-equal eigenvalues. So we're done. So therefore, we can divide by lambda minus mu, and we get v dot w equals 0. Any questions at all about this proof? Do you remember in that example problem? The exercise you guys asked, we found the eigenvalues and they were not orthogonal. Should we worry? Why do we not get orthogonal vectors?
It was in a symmetric matrix.
Right. This A is a symmetric matrix is absolutely important. If you don't have a symmetric matrix, then good luck. It usually won't be orthogonal. But if you do have a symmetric matrix, you always get orthogonal vectors for the eigenvectors. Any questions on this big theorem? Okay, let's go to the next one. Kind of today's theorem day. There's a whole lot of theorems in this section. If A is skew symmetric, do you remember what skew symmetric is?
A equals the negative A transpose.
Yeah. So that means if you take the transpose, you introduce a negative sign. And V is an eigenvalue of A, then either V is 0 or V is not real. Okay. So, and not real, by the way, means complex, like 3 plus 5i or something. All right. So we can write down, and today's a theorem and proof day. We know that A equals negative A transpose. So we know that's true, right? So the question is, why can't you have a real eigenvalue that is non-zero? So why can't 7 be an eigenvalue, for example? What can I do to both sides of this? Probably V is a bad letter. I can use X instead. Or sorry, lambda. We have eigenvalues. Sorry about that. Much better. So why can't you have? So what happens if you have 7? What can I do to this equation? Okay, what I can do is I can multiply both sides on the right by V. Any questions on that so far? Okay, what's next? What's AV?
Lambda V.
Yep, so it's lambda V. Okay. That's equal to negative. What's A transpose V? Okay, so then we're going to have to find what's A transpose V. Okay, can A transpose V? So the question is, can A transpose V be negative lambda V? The answer is no. So this is something that's not negative lambda V. Any questions on that? Okay, because if it was, then A would be symmetric, and it's not. So that means that we're done. So that means V must be 0. Sorry, lambda equals 0.
Are the eigenvalues going to be entirely different?
Yeah, I mean, they'd have to be different. They can't all be the same because then you'd have A equals A transpose. Do you see? But
Yeah.
A is not equal to A transpose, so they're different. And if they're different like that, then you got a problem. So therefore, we know that lambda must be 0 or it could be complex. Therefore, lambda, let me get lambda. Okay, next theorem. A lot of theorems today. If A is symmetric, then A is orthogonally diagonalizable. We already had this one before. Do you remember? I was kind of going through the book and making sure we have all the theorems that the book goes over. So if A is symmetric, then A is orthogonally diagonalizable. Thus, there exists an orthonormal set of n eigenvectors. Okay. Do you remember that? So it's a big theorem. That's why it's said twice in 2 different sections. But I'm going to move on because we've already had it. But I want to remind you. Okay. If A is a matrix with n real eigenvalues, then determinant of A is a product of the eigenvalues, and the trace is a sum. Okay, maybe I'll prove the first part. Okay. How do I know the determinant is a product of the eigenvalues? Well, let's go for it. So the determinant of A equals, well, if we have n real eigenvalues, then how can I make A nicer? In one big long word.
Diagonalize.
Exactly. So that means that I can write this as P D P inverse. And then take a determinant. Okay, but then we have a big theorem that the determinant of P D P inverse is a determinant of P times the determinant of D times the determinant of P inverse. Any questions on that? All right, but what's the determinant of P times the determinant of P inverse?
That's just 1.
Yeah, that's 1.
Yeah.
That's 1, because the determinant of P times the determinant of P inverse is the determinant of P times P inverse, which is the determinant of I, which is 1. So that's equal to the determinant of D. But what's the determinant of a diagonal matrix?
The multiple of all the diagonals.
Yep, the product of the diagonals. But what are the diagonals of D since we've diagonalized? Do you remember how you get the diagonals of D?
The eigenvalues.
Yeah, those are the eigenvalues, which is the product of the eigenvalues of D. Any questions on that? And that's it. I guess I didn't write the word proof. Any questions on that? Like I said, a lot of theorems. Here comes a big definition. Kind of important words. So let's suppose A is an M by N matrix. All right, we just changed everything. Okay. By the way, what's the determinant of A? See if you're paying attention.
There isn't one.
Good. That means you're paying attention. If A is not a square matrix anymore. Now let's say we have a non-square matrix or possibly non-square matrix. So if A is not square, you can't even think about determinants or eigenvalues or eigenvectors or any of that stuff. On the other hand, you can take A transpose times A. Remember, A is M by N. A transpose is N by M. So A transpose A is N by N is square. Do you all see that? So A transpose A is a square matrix and always will be. Then the singular values of A are the square roots of the positive eigenvalues of A transpose A. Any questions on what this is saying? So it's the square roots of the positive eigenvalues of A transpose A are the singular values, and they're important. Any questions on the big definition?
What are the singular values again? I forget.
That's what they are. They're the square roots of the positive eigenvalues of
Oh,
A
okay.
transpose A.
Okay.
There's a definition. So
Oh,
there
okay.
it is. Yeah, if you forget, that means you forgot what I said 1 second before you asked the question.
Yeah. I was like, wait, are the singular values the square roots, or are they actually in the matrix? Like, no, wait. The singular values are their own thing.
Yeah. This is not a review of anything. This is a new definition. Okay, they just happen to come up from time to time. Question? Okay, so those are singular values. Okay, so now comes the first theorem about it. Okay, let's suppose we have an M by N matrix A. Then we could look at A transpose A. We could also look at AA transpose. Do you agree that they are both square? A transpose A and AA transpose? Can you see it? That they're both square matrices?
Yeah.
Yep. Okay. Yeah, they're both square matrices. By the way, can you multiply these two? Can you multiply A transpose A times AA transpose?
Yeah.
One more guess?
No.
No, they're square matrices, but they're not the same dimensions. Right? So A transpose A would be N by N, and AA transpose is M by M. Do you see that? So they're not even the same dimensions, these two matrices, but they have the same non-zero eigenvalues. Pretty cool, isn't it?
The eigenvalues will be the same, but not the eigenvectors, right? Most likely anyway.
Right. I mean, if M is not N, not just most likely, it'd be impossible. They're not even in the same universe, right? The vectors. So if M and N are different, then A transpose A will be a N by N. So that means that the eigenvectors will be n-dimensional eigenvectors, whereas AA transpose will be M by M. So those eigenvectors will be m-dimensional eigenvectors. So they're not even the same dimension. You can't even talk about them being the same. I mean, doesn't even make sense to compare them even. Does that make sense?
Yes.
But the eigenvalues are numbers. You can always compare numbers. And it turns out the numbers are the same. Any questions on this theorem? Okay, by the way, how do you show it? Any thoughts? It's actually quite easy.
Start with the definition of an eigenvalue.
Exactly. So I'm going to take A transpose A times V equals lambda V, right? What can I do to both sides?
Left multiply by A transpose A inverse.
Okay, there's a problem with that. What's the
Okay.
problem? Can you always find the inverse of a matrix?
Not always.
Not always. In fact, often not. So you can't just say, I'm going to take the inverse, because there may not be one. Does that make sense?
Yes.
Yeah, so you got to be careful about doing that kind of thing. Okay, so we can't do that. Okay, so don't even try. Okay, but what we can do is we can say AA transpose equals something like that. And we can talk about, we could transpose these guys. Do you see? So we can take A, we could left multiply on A, in fact. That we can do. So I can write A transpose AV equals A lambda V. But A lambda V is lambda AV. Do y'all agree? Any questions on that? So now, just to emphasize what what we're looking at is I could put parentheses around the AV. Any questions on that? Why am I done? It's tricky, but I'm done. Let's see. We have AA transpose times a vector equals lambda times that vector. That means lambda is an eigenvalue. So if lambda was an eigenvalue of A transpose A, lambda is an eigenvalue of AA transpose. We're done. Any questions on that theorem? So it's a nice little theorem used here and there. Okay, next one. Today's theorem day. Oops. This one. Okay, let's suppose we have an M by N matrix, not necessarily square. Then there exists orthogonal matrices U and V such that A is equal to U sigma V transpose with sigma of the form sigma equals sigma 0, 0, 0, where sigma is a diagonal matrix with singular values along the diagonal. So I'm not going to prove this, but I want you to look at this for a while. Any questions on this? Any questions? So notice the 3 zeros here in this matrix. These are not numbers. What are they?
Are they vectors?
No,
Matrices?
they're matrices. Okay. So let's say sigma is a 2 by 2. If this guy here is a 2 by 2, then this 0 is 0, 0, 0, 0. It's the 2 by 2 matrix of zeros. And so are these guys. Do you see? To make it work. So that's just a note. Be careful about looking at that 0 and thinking of it as a number. It's a matrix of all zeros. Any questions on this idea?
So you can have a matrix of composed of matrices?
Yeah, you basically just get rid of the parentheses inside. That's all that is.
Okay.
Right? You know, in fact, I think I have one up here I'll just talk about because I have examples written. Here we go. So for example, I don't know, this one here. So you can think of the negative 12, 3, 3, negative 9. You can think of that as a 2 by 2 matrix. Any questions on that? And this 0, 0 here is the 0 matrix. And so is this the 0 matrix, but it's a 1 by 1. Does that make sense?
Yeah.
Yeah, it's just a way of thinking. That's all it is. You know, not really doing anything. Okay, I'm not coming up with this either. It's just as standard. Where was I? Okay, so this is called the singular value decomposition. Because what it does is it allows you to write it in kind of a nice way. By the way, are U and V of the same dimensions? What do you think?
Probably not, because A is an n by n matrix and not a square one.
Exactly. U and V are definitely not. I mean, unless M equals n. If M's not n, then U and V are not even the same dimension. So be careful. Any questions on this idea? Okay. Now comes a big theorem. And that is if A is an M by n matrix, then we've already had the first part. Rank of A equals rank of A transpose. Do you all remember that one?
Yes.
Okay, that came like in week 3 of the class or something like that. That was pretty early. Okay, here's what's new. The rank of the matrix is equal to the number of singular values. Okay, so the rank of this matrix is equal to the number of singular values. Why is that true based on the above theorem?
Because the singular values are in the diagonal.
Yeah, so if you look at sigma, sigma, definitely capital sigma, has the rank equal to the number of singular values, because this is a diagonal matrix with singular values along the diagonal. Is that clear? And orthogonal matrix, multiplying by an orthogonal matrix doesn't change the rank, right? Is that clear? That's the good thing about orthogonal matrices. They're bases for the space. Multiplying by a basis doesn't change anything. Okay, it doesn't change the rank. So that's it. That's the whole proof right there. There's nothing really to say. Okay, so the number of singular values of the matrix A is the rank of A. Any questions on this theorem? All right, here comes a definition. And then maybe I might go to the book and do some examples. I think this might be the best way. A matrix is called positive. Oops, that should be in red. It's called positive, or in parentheses, negative definite, if all of its eigenvalues are positive, if it's positive definite, negative, if it's negative definite. Any questions on that definition? Okay, so if all of its eigenvalues are positive, it's positive definite. If all of its eigenvalues are negative, it's negative definite. Is that clear? Okay. Now comes a big theorem. If A is positive or negative definite, then A is invertible. Okay, by the way, does that tell you that if A is invertible, it must be positive definite?
No.
No. Can you think of an example? Of a matrix that's not positive definite, not negative definite, but still invertible?
Zero, 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 like the zero matrix.
Yeah, the zero matrix. No, the zero matrix is not invertible. Good luck. The determinant's zero. You have no chance, right? So no, that one doesn't work, actually.
I'm thinking of transposable. Sorry.
Transposable is a whole different thing. Every matrix is transposable. You can take a transpose of any matrix because that's just a simple definition. But how about just 1, 0, 0, -1? It's diagonal. Its eigenvalues are 1 and -1. So it's not positive definite. It's not negative definite. Does that make sense? But it's definitely invertible. It's its own inverse, actually. Okay, because the determinant's non-zero. So that's the first thing is, this is a one-way theorem. It's not a two-way theorem. Is that clear? You can only go from left to right. So how do we show that if it's positive definite, then it must be invertible? Any thoughts?
You could take the determinant of that matrix.
Yeah, I can take the determinant of the matrix. Now, and we want to see what might that determinant be. Well, if it's not invertible, what must the determinant be?
0.
Yeah, so this is proof by contradiction. So we suppose that we suppose it's not invertible, and then we prove that it's not positive or negative definite. So suppose A is not invertible. Then the determinant of A must equal 0. Okay, what do we know about one of the eigenvalues if the determinant of A equals 0?
One should be 0.
One of the eigenvalues is 0, right? Because that means if the determinant of A is equal to 0 by TFAE, then we know the null space of A must be non-trivial. So that means there is a vector V such that AV equals 0. So that means AV equals 0V, or 0 is a eigenvalue. Okay, so, and we've had that theorem as a theorem before, but therefore it's not positive or negative definite. Definite. There we go. Any questions on that? I think it wants a comma. Any questions on the proof? It's a very simple proof, but only if you understand it. So kind of positive, negative, definite are nice because if you have it, then you know you have an invertible matrix immediately. Any questions on the theorem? Okay. Now this comes up a lot, and that is, let's suppose we have a symmetric matrix. Then A is positive definite, okay, if and only if V transpose AV is greater than 0, let's put out its own line, for all non-zero V. This is used a lot. Okay, so if A is symmetric, then we can always say this. Okay, what's nice things about symmetric matrices?
The inverse is a transpose.
No, that's orthogonal. Yeah, symmetric matrices don't always have the inverse being the transpose, right? But what do they always have?
Same determinant.
As what?
As the inverse of the...
Symmetric matrices aren't always invertible even. right? The 0 matrix is symmetric. Let's say 2 by 2, 0, 0, 0, 0, 0. Starts with a D. Symmetric matrix is
Diagonalizable.
yes, diagonalizable. Okay, so that's what we know. We know symmetric matrices are the diagonalizable matrices, right? So it's positive definite if and only if V transpose AV needs to always be positive. Okay. Now, the idea here is if A is symmetric, we can diagonalize the matrix. So basically, we can change the basis and make A diagonal such that you get the eigenvalues, right? Any questions on that? And then we can also change our V's into that basis also. So basically, we can go into a new basis where A is diagonal and just let A be D. So use a basis that diagonalizes A. Then A is equal to D. But what is V transpose dV? What does it mean when you do V transpose dV? Any ideas? Any thoughts? So let's look at, let me do an example, and I think that'll help you if you don't see it. And then you'll be convinced once you see the example, I think. I think it's worth it to see an example. Just got to get there. How about a 3 by 3? So let's say V is 2, 3, 4. Just making some numbers up. So there's our vector V, right? And then we're going to multiply it by a diagonal. And let's say we don't have a positive. Let's say we have something that's not positive definite, just for fun. But is diagonal. So how about -1, 0, 0, 0, 2, 0. Let's make that 5 instead of 2. Just wanted to have unique numbers. 0, 0, 1. And then we're going to multiply that by V transpose. So that's 2, 3, 4 on its side. Whoops. One more try. There. Okay, so we want to multiply. What is this matrix times 2, 3, 4?
-2, 15, and 4.
Yes, but I'm going to write it a little differently because I want to emphasize what happened. It's going to be 2 times -1 up there. And then 3 times 5. And then 4 times 1. Any questions on that? All right, well, now this is an easy matrix multiplication. When you have a matrix multiplication, which is a horizontal vector times a vertical vector, that's a dot product. Do y'all agree?
Say that one more time.
If you have a horizontal vector times a vertical vector, that's a dot product.
Yeah, okay.
Yeah, there's nothing to it, basically. So that's going to be 2 squared times -1, and then plus 3 squared times 5, and then plus 4 squared times 1. Are y'all following? Y'all believe it?
Yes.
All right. Now, so that's what happens when you take V transpose AV in its diagonal basis, right? Principal axes, they call it. All right. So notice the 2 squared, 3 squared, and 4 squared are all positive. Do you agree? No matter what I started with, even if I started with -2, -3, -4, when you square it, you get a positive number. Is that clear?
Yeah.
Okay. So if for all vectors V, you get a positive number, well, we can let V be 1, 0, 0, and then you just get 1 times -1, and that'll grab this first diagonal entry. Do you see that? If I let V be 0, 1, 0, that'll grab the second diagonal entry. And if I let V be 0, 0, 1, that'll grab the third diagonal entry. Well, if it's always positive, that means all the diagonal entries have to be positive. So therefore, A is positive definite. And that's the proof in kind of both directions, because you can go either way. Any questions on that? But I thought I'd show you with actually a physical matrix. Without so many letters, you get lost in all the letters. Hopefully you didn't get lost in the numbers. Any questions on this idea? Okay, so the last big theorem, before we do some example problems maybe out of the book, I thought, is called the Cholesky factorization. Okay, named after some guy named Cholesky, who I've never heard of. My guess is from Russia. I don't even know, but it sounds right, doesn't it? And that is the following. Let A be a positive definite matrix. So do you remember what positive definite means?
All eigenvectors or eigenvalues are positive.
Yeah, all eigenvalues are positive, okay? So then there exists...
I just looked it up. Sorry, I didn't mean to interrupt.
What's that? Okay.
Cholesky was French.
Oh, really? Cholesky?
Yeah, it sounds weird, right?
Yeah. Like I'll tell you what I'm not. I'm not a math historian. So never trust me about anything. You know, I told you I'm guessing Russian. I have no idea. French sounds good. Okay. Yeah. So math history was never my specialty. Okay. But if we have a positive definite matrix, then there exists an upper triangular matrix U. Do you remember what upper triangular means?
It means that the bottom right of the diagonal is zeros, and then the top right has any actual numbers, and then the diagonal is like whatever.
Yeah, diagonal can be whatever it is. Exactly. So that's what an upper triangular matrix is. It means all the non-zero stuff is up at the top. Okay. Top of the triangular. Okay, of the triangle. Okay. So there exists an upper triangular matrix U whose main diagonal entries are positive. So now we actually are talking about the diagonals being important, and they're all positive, such that A can be written as U transpose U. And this factorization is unique. By the way, what is the transpose of an upper triangular matrix? What kind of matrix do you get?
A lower triangular matrix?
Exactly. Exactly. So if you start with an upper triangular matrix, take its transpose, you end up with a lower triangular matrix. So what this says is that if you have a positive definite matrix, then you can always write that matrix as a product of a lower triangular matrix times an upper triangular matrix. Okay, and if you did it and someone else did it, and you compared your U's, what are you going to notice?
Will be equal.
Yeah, you have the same. You'll have the same. There's only one answer. It's kind of like RREF. Remember, RREF was unique? Because if you start with a matrix and I RREF it today, and then tomorrow I RREF it again, I'm going to get the same answer. Okay, whereas diagonalization is not true that way. Okay, there's lots of choices for diagonalization. Because remember, you can choose any order of eigenvalues, for example. And eigenvectors, you have lots of choices for each eigenvalue. You can multiply by any constant, any non-zero constant. But when it comes to Cholesky factorization, there's only one answer. Okay, any questions on this big theorem about Cholesky factorization? Any questions? Okay, I do want to let you know something about the syllabus. Kind of going fast today, but there's a reason. Is that if you look at the syllabus, you will see that a week from today we have an exam. And what we've got is 7.4, which we're in now, is supposed to be talked about today and Wednesday. And I actually did more than half of it. Okay, I went kind of fast today, but there's a reason. That way on Wednesday, I can finish 7.4, start the stuff for the following Wednesday, and then we can have a little more time to review for the exam. Because my guess is you probably want a little extra time to review for exam 2. So Friday, I'll do some review for exam 2, and we'll do the probably 9.1 half and 9.2. So that's the plan in terms of what's going on. Any questions so far?
I know we're not there yet, but I was thinking to myself, is our final going to be cumulative?
Yes.
Okay.
Yeah, final's definitely cumulative. But the good news about this class in terms of the final being cumulative is that, and hopefully you've noticed this class builds on itself, doesn't it?
Oh, yeah.
I mean, if you don't remember the first week when we RREF to matrix, and you don't know what RREF matrix, RREF means, good luck doing anything. Do you agree? Okay, and you need to know how to add matrices and multiply matrices. Remember we did that at the beginning? So most of the stuff we did at the beginning we're redoing anyway. There's some like chemistry equations and stuff like that we don't repeat, but most of what we do we repeat anyway. We reuse. So it's not that big a deal. It's not like other sections where it matters a lot. But what I want to do, since we got another 5 minutes, is I want to do one problem. And I'm going to let you choose. And so pick any problem from, we're in 7.4. I'm scrolling. I know you can't see me scrolling. It takes forever just to get to where I want to get to in this book. The section goes on and on and on. So pick a problem from 7.4 and we'll do it. Could even be a homework problem if you want. Hopefully one of the first, half of the problems instead of something that's not due till Friday.
How about number 3?
Okay, so number 3. I finally got to it. Okay, so let me go grab it. Because I did a lot of theory today, but now I get at least one chance to do a practice problem. Maybe this works. We'll see. It's really hard to use Zoom and multiple programs at the same time. That one, I think. There we go. Sorry, I'm moving Zoom windows around. There we go. That one, right? So find the eigenvalues and an orthonormal basis of the eigenvectors for A. That one. Diagonalize A by finding an orthonormal matrix U and a diagonal matrix D such that U transpose AU equals D. Okay, hint, one eigenvalue is 2. So what do?
Well, we need the determinant of A minus lambda I.
Yeah, so I take the determinant of A minus lambda I, and then hopefully I get something that's not too horrible. Sound good? So let's do that, and let's pop it in. Sorry, I gotta move my Zoom stuff so I can get to stuff. Got it. So determinant of, and now of that guy. So I need to subtract 1 from all the diagonals, and I get -2. 1, 1, 1, -2, 1, 1, 1, -1. Okay, by the way, how do I know this is, I'm actually going to be able to orthogonally diagonalize this? What theory tells me that? In one word? This should be -2, huh?
Should be symmetric?
Yeah, it's symmetric. Is it clear that A is a symmetric matrix? Take the transpose, you get itself.
Yeah.
Okay, so now let's go and do this. Kind of a pain. Oh, wait, I'm sorry, not -2. That was a mistake. -1 minus lambda. Yeah. That's what we need. And -1 minus lambda. And then -1 minus lambda. It's kind of a pain. All right, so let's do it. So I'm going to get -1 minus lambda times, and now I'm going to have -1 minus lambda squared minus 1. Okay, and then I'm going to have a minus row or column. It really doesn't matter. There's no zeros, so I'll just do the first column. So then -1, and then times, if I get rid of the second row first column, I get 1, 1, 1, 1, -1 minus lambda. And I take the determinant of that, I get -1 minus lambda. -1. And then we have a +1. And now we're going to get rid of the first column, third row. And I get 1 minus -1 minus lambda, which is 1 plus 1 plus lambda. Any questions so far? Okay, getting there. It's kind of messy. All right, so take a look. What do I have so far? Might want to write it out. So that's equal. Oops, not a matrix. So what I get, I have negative 1 minus lambda. Times, let's FOIL this out and simplify. So we're going to have a lambda squared. And then we're going to have a minus 2 lambda. No, sorry, it's plus 2 lambda. And then we're going to have a plus 1 minus 1. So that goes away. And then plus. And this gets interesting. Notice that all these minuses go away. And these terms are the same. And you just get twice lambda plus 2. Any questions on that? All right, notice that the lambda squared plus 2 lambda is lambda times lambda plus 2. I can factor the lambda plus 2. And when I factor the lambda plus 2, I get lambda times 1 plus lambda. And that's a negative plus 2. Any questions on that? Getting there. So what I get? So I get lambda plus 2. And then we have, I can factor negative 1 out. We get lambda squared minus we get lambda squared plus lambda minus 2. So that gives you lambda squared plus lambda minus 2 is lambda plus 2 lambda minus 1. All right, so what are my eigenvalues?
-2 with multiplicity of 2 and 1.
Yeah, so I'll put a 2 for multiplicity of 2 and 1. Okay, which is good because they told us one eigenvalue is -2. So we got that one. So we got what they asked us to get. All right, we're out of time, but at the next point, what should I do?
Now find the eigenvectors.
Yeah, now we find the eigenvectors. And for the -2, we'll probably have 2 linear independent eigenvectors. Okay, and then we'll have the 1, and then we diagonalize. Okay, and make sure it's orthogonally diagonalized. So that means we may need to use Gram-Schmidt when you're getting the 2 vectors with a lambda equals -2. But I am out of time, and I try not to go too much over, and I went over a bit. So sorry about that.